That's what the brain does. And we want to know how it does that. And so the way we approach this problem is we use neuroscience, the anatomy and physiology of the brain, as a very strong set of constraints. We're not just trying to invent intelligent computers. We're trying to understand how the brain does this. How does the brain do this? So we have to look at the constraints that the brain provides. And I'm going to talk about that. And then we add theoretical constraints on top of it. So let me just go back to my model here. We're going to give you a little neuroscience lesson, okay? And then if it gets, I hope it won't go too deep. And then we'll get back out to fun stuff. So go back to this sheet of cells. We know a lot about this sheet of cells. It turns out that everywhere you look here, the cells it looks very similar. There's different sort of the same sort of structure everywhere in the neocortical sheet. And there's 6 layers of cells, and they have the same cell types and so on. But the most notable thing about the neocortical sheet in your head is it's divided into regions that do different things. So there's areas that are dealing with vision and language and hearing and touch and all kinds of other stuff. These regions are connected together through bundles of nerve fibers. So if a region connects from A connects to B, we know also that B will connect back to A. They're reciprocal, but they're asymmetric, meaning we can tell which is the feed-forward direction and which is the feedback direction. Now, you can take a lot of years and take a particular mammal, map out all the regions of their neocortex, map out all the region connections between regions, and you can make a map. And this has been done, very difficult work, and this has been done for a series of animals. I'm going to show you the map for the macaque monkey. Now, before you say, oh my God, what's this all about? This is, first of all, a famous diagram for neuroscientists. And the second thing is it's really not that bad. And third, you don't really need all the details. But I'm going to give you some highlights of it. Now, you can pretend this is your brain, because we're not that different from a macaque monkey, and we can't do these experiments on humans, but this is pretty close to you. So now, let me just explain what I'm showing here. There's these little rectangles all over this picture. Those are the regions of the neocortex. Those are the different regions of that sheet. The lines show how they're connected together. So every line is a feed-forward and a feedback direction connection. In this particular drawing, sensory patterns coming from the bottom, and so feed-forward is going up and feed-backward is coming down. On the right, we have regions associated with vision. On the left, we have regions associated with motor and sensory behavior. And they're connected together at the top. So this is the map of the macaque monkey's neocortex, or at least a good portion of it. Now, already we can say some very interesting things about this. First of all, remember, this is a memory structure in some sense. It's a model of the world, about how the world looks and behaves and so on. So we can say some things about how information is stored in this model. The first thing we can say is information is stored, or knowledge is stored, in a distributed fashion. If I want to ask you, like, well, where do you know what a dog looks like? Or what President Obama's doing or whatever, you're not going to find it in a particular region. It's going to be distributed throughout, because information has to flow through many, many regions to get anywhere. And if you follow sort of modern neuroscience, you see these studies now where they show which brain region lights up when you're doing different things. It's very misleading. They're only showing the region that's lighting up the most. But when you do anything, a whole bunch of these regions become active all at once. So anyway, information is distributed in a hierarchical fashion. That's not like we do it in computers. The second thing we can do is we can say the system is self-training. When you're born again, this structure is there, but the knowledge of the individual connections is not. And so this thing has to learn. Each of these regions has to learn to store something about the world, and we can't program it. It has to learn purely through sensory patterns. Even when your mother or your father or your teacher was teaching you things, they were still going through the sensory. There was no direct input into the brain. So it's a self-training system. And then the last thing here is very, very surprising. It was known for many, many years that these regions look nearly identical. There are some differences, but they have a tremendous amount of commonality in terms of the cell structure and how they're connected together and so on. And so if you looked at one region at the top of the visual hierarchy and the bottom of the auditory hierarchy, if you just look at the details, it looks almost identical. And it was 30 years ago, a physiologist named Vernon Mountcastle who proposed that actually, not only do they look the same, but they're actually doing the same thing. Each region is doing the same thing. And what makes a visual region do visual things is what it's connected to. And an auditory region, auditory, is what it's connected to. At first, scientists couldn't believe this. It seemed impossible. How could the brain solve language the same way it solves vision, the same way it solves somatosensory or touch? But it's true. There's an overwhelming preponderance of evidence that suggests this is true. And so that makes, as a theoretician, this makes our job a lot easier. Now we have a system with a whole bunch of these things that are doing the same thing, arranged in a hierarchy, learning on their own, and so on. Now, I'm going to give you a few more details here. I'm just going to highlight some regions. These are in yellow. These regions are part of the primary visual pathway called the ventral pathway, and those are the most important ones for recognizing what things look like. So I'm now going to show you I'm going to show you the same regions, but I'm going to show you how big they are. This diagram doesn't show you how big they are. So now I'm going to look at all those visual regions and just see how big they are. And the yellow ones are, again, the primary visual pathway. So here you see that the first regions, the ones closest to the eye, are huge. In the macaque monkey, they represent 25% of the volume or the area of the neocortex. That is 25% of what the brain knows about the world is low-level vision information. And you can see that it gets narrower, it gets to the top. You might think that, we have all these high-level concepts, we need big regions at the top. No, it turns out you actually have a lot of big regions at the bottom, near the sensory input. So this is kind of surprising. You wouldn't have thought that. Now, finally, you might say, hey, what's going on here? This looks like a flow chart. Information comes in and goes chunk, chunk, chunk. That's misleading. So I'm now going to show you another picture that's more reflective of what's going on. These are just the main visual regions of the brain. And again, this eye input's coming in from the bottom. And what you see here is it's more like the bottom regions, a lot of little regions. And that it's more like a tree. It's like an inverted tree. And they converge as you go up the hierarchy, and they diverge as you come down the hierarchy. Now, as a computer scientist, this says something. This is a memory structure. This is the design of a data structure, if you will, for how the brain stores information. Now, this happens to be the visual information in your cortex, but you have similar hierarchies like this in your auditory and somatosensory or touch regions. In fact, all information stored in the neocortex is stored in a hierarchical tree-shaped structure like this. And they vary in size and how many neurons and so on. There's a lot of variation, but the basic idea is the same. So now we have to ask ourselves, well, geez, if we can figure out what each of these regions is doing and how they work together, then we have a good theory, don't we? Then we sort of have a theory about how the brain learns and how it forms representation about the world. So we have a theory like that. It's actually pretty simple. And I'll just give it to you in one slide and just dump it on you, okay? So we call this theory hierarchical temporal memory. By the way, this doesn't come out of the blue. There's a lot of other people who are working on similar ideas. So this is the term that my lab and my people I work with use, hierarchical temporal memory. So the first thing we can say was, what is each node, remember, each little region of the neocortical sheet, each part of that napkin doing in that hierarchy, each of those little boxes? Well, it's pretty simple. The first thing they do is they learn common spatial patterns, things that happen at the same time. So if one input and another input happen at the same time, more than chance, we can say there's likelihood that they have a common cause in the world. The dog barks and you see the dog, you hear the sound, you see the dog, they probably the same thing. The second thing it does is it learns sequences of those patterns. It's like learning melodies. And the idea here is that if you see things that occur together in time, one after another, often or more often than chance, there's a good chance that they have a common cause in the world as well. And you can think it's like learning a melody. I hear that series of notes over and over again, I learn to represent the melody. Now, what a node does is it passes the name of the melody, the name of the sequence, to its parent in the hierarchy. And the parent does the same thing. It looks for spatial patterns of sequences and then sequences of sequences. And so what happens here is where you have a very fast-changing pattern, like my speech, which is occurring on the order of milliseconds, coming in the bottom of your auditory hierarchy. As you go up, your brain is recognizing things. Oh, that's a phoneme, that's a word, that's a phrase, that's an idea. And you get to the top and you see neurons that respond to slow changes, and that's what we see. The other thing that each node can do is it can pass down a prediction. Basically, since they're remembering sequences, they always can predict what's going to happen next in a probabilistic fashion. They can't do it exactly, but we have a sort of a probabilistic thing saying these are the things that are likely to happen next, and it passes out to the child node. And if you take a slow-changing pattern at the top of the hierarchy and you unfold its sequence, and each of those elements unfolds into a sequence and so on, it can generate a pattern like my speech or a very complex motor behavior. So that's the basic idea of what each node is doing. Now, how do the nodes work together as a whole? Well, if you put them together in this way and you do all the proper training and so on, what it does is it creates a hierarchical model of causes in the world. It's a model of the world, but it's hierarchical. It remembers little things in small spaces and big things on top of it and so on. We use a technique called Bayesian belief propagation, and some of the scientists and other people in the room will know what that is, but many of you will not. It's a simple mathematical technique that was invented a while ago. It's beautiful, actually, by Judea Pearl. And it shows how you can have a network of nodes like this, and they don't know what each other's doing, but they all collaborate to very quickly come to common agreement about things. So you can put what it basically means is I can put a belief or a pattern on some set of nodes, and in a single pass of the system, all the other nodes will form a sort of copacetic set of beliefs. And that's what happens when we look at the world and see the world and so on. We basically get this noisy input, and it works in very noisy inputs, and we say, what is the most likely cause of all this? So at the top of your brain, you perceive the world very cleanly. Like you perceive me as very clean, and I'm on a stage, there's no doubt about that. But if you actually looked at the data coming into your brain, it's very messy. And Bayesian belief propagation makes it very clean when it gets to the top. So that's the basic of the theory. Now I'm going to show a few really technical slides, okay? But I'm not going to ask you to understand them. But I just want to give you a sense for what it is that a theoretical neuroscientist like myself does, and my colleagues. So this is a picture of a single node, a single little area of your neocortex, expressing what it does in the language of belief propagation. And I won't bore you with it, but essentially you have these messages that come in and go out, and there's these 4 different boxes here, and one's labeled, 2 of them are labeled Markov chains. Those are just a fancy name for sequences, and the other 2 are labeled coincidence patterns. That's a fancy name for spatial patterns. And anyway, you can look at a standard belief propagation node this way. Excuse me. You can define the equations for what these boxes are doing, and I really won't talk about that. There's a bunch of little equations up here. And then you can map those equations back onto the neuroscience. You can say, well, these equations must be being implemented somehow in the brain, and therefore can we map them onto the actual neurons that we know exist? And this is a sort of a prototypical or archetypical diagram of a section of the cortex and 6 layers of cells and the different cell types and so on. This is straight neuroanatomy. And you can map these equations on it, and you can make predictions about what neuroscientists, experimental neuroscientists, should see. And we're doing that. Okay. Now, we've taken this theory and we've implemented it into a technology, or at least we're trying. Gar might have given you the impression that we're really, this is almost done. It's not. We're at the very beginning of this, very beginning of it. But we're looking at how to build this in software, and we've done this, and then apply it to different problems. So these are different problem areas that people have come to us, and we've worked on a bunch of these. We've worked on voice recognition, we've worked on some digital pathology, we've worked with some automakers, we're starting to do some fraud detection in bank. We're trying to figure out what the technology is good for and where it's going to work, and it's a very difficult problem. It's not so simple. So this is sort of a class of problems. Now, and all these things have the same thing in common. They have a lot of data, and you're trying to discover the underlying causes of it. Can I discover the underlying causes? Can I detect patterns of fraud in banking situations? Can I detect patterns of attacks on networks and things like this? And can I just see what are the typical patterns that these things exhibit? Now, we've spent most of our time doing vision, computer vision, and that's because everyone knows computer vision. Gar works in computer vision, and it's a well-known area. And so it gives us a lot of benchmarks to test ourselves and so on. So I'm now going to give you a few little demos here. Is that the next thing you might talk? Oh, no, yeah. I'll come back to that in a sec. I'm going to talk a little about vision, but I don't want you to think that all we're doing is computer vision. This is the area we're working on. So in the computer vision thing, I have a computer science friend of mine. It was a professor at Cornell, Dan Huttenlocher. And he proposed a number of years ago that we create a grand prize in computer vision. We put up a large prize, like $1 million. We'd propose a prize which would be very challenging, no one could do, but maybe they could do in 10 years. And if someone met that challenge, they would get the prize. So I said, Dan, what should the challenge be? Now, you might find this hard to believe because you might think this is so simple, but this tells you the state of computer vision. He said, we should make it a computer that can recognize cats from dogs. That's worth $1 million. And now here's some pictures of cats and dogs. I assume that you have no problem telling me which is a cat and which is a dog. A 5-year-old can do it. How hard can that be? Boy, $1 million, huh? But the computer's got to do it, not the child. So you might say, well, if you didn't know any better, you weren't listening to me speak, you say, well, how would I go about solving this problem? You might say, well, we'll come up with a definition for a cat. Cat has short noses and they got pointy ears and whatever. And another sort of definition for what a dog is. That doesn't work. It just doesn't even come close to working. There's exceptions. You can't even tell. You can't even know where there's an ear here. These images are impossible to understand. And then you might say, well, oh, I'll just take an image of a cat and an image of a dog, and I'll try to figure out a new image, which is closer to the image of the cat or the dog. You can't do that. There's no transformation you can do to turn one of these dogs into another dog, at least no regular transformation. There's no mathematical equivalence between these dogs and cats and so on. You might say, well, I'll just remember every dog and every cat I've ever seen, right? Well, there's two problems with that. That could theoretically work. There's two problems with that. One is you don't have enough time because you have to see a gazillion billion dogs and cats because there's always more that you haven't seen, and you don't have enough memory in your brain. You just don't. So you don't have enough time, and you don't have enough memory, right? So, but in a sense, that is the answer. And the way these hierarchical temporal memories work is they store a lot of information, but they do it in a very efficient way. They do it in an efficient way that says, look, I'm going to remember almost everything I see, and you remembered a lot about the world, but I'm going to be able to generalize when I can, and I will do it in an intelligent way. And I'm just going to leave it at that. And that's a solution to this problem. As all good engineers, I'm an engineer, as well as a neuro guy, and we want to build things, right? So I'm going to tell you how we went about this. This is 4 years old. So this is not new. This is old. 4 years old. Well, the first thing we did is we started with a very simple vision problem. And actually, this work belongs to a colleague of mine, Dilip George, who's the co-founder of Dementa. So I'm talking about his work here. He said, OK, let's make a very simple vision system. This vision system has a retina, if you will, or an image space of only 32 by 32 pixels. And we have 3 layers to our hierarchy. We have 64 nodes at the bottom layer. Each node is looking at a 4 by 4 pixel patch. Then we have 16 nodes above that and 1 node above that. This is our miniature little microcortex. And then we trained it on these little patterns. These are little line patterns. We made movies of them. So we take these little patterns, 48 of them, and we make movies, and we just expose it to this memory system. And we learn by the principles I just explained. And then we could show it novel patterns, and we say, OK, what do you think this is? And these are all novel patterns. They're novel in the sense that they're distorted, they're noisy, they're different sizes. You can see on the left we have something we call a dog. It's facing left and it's facing right. Now, this is a toy problem. I understand that. But it's a very difficult toy problem. And this system is almost unbeatable. I mean, you can download it and play with it. It's really good. But it's a toy problem. You can see the maybe you can see the 5th column over is something called a helicopter. It's a little line drawing a helicopter. You'll see that again in a second. So the next thing we did, we said, well, this seems to work pretty well. But remember, this is all a system about time, and we store sequences of patterns. In fact, mostly what you recognize in the world is based on time sequences, not spatial patterns. So we said we should be able to do the same thing here. So the first thing we did, we took a pattern and we stuck it in a noisy field. Now, there's a helicopter in this little picture. It's on the bottom. You might be able to see it. And it's surrounded by a field of random noise. And if we fed that into our HGM, we found that it didn't do very well, but it did OK, actually. It got about 20% right, which is still pretty good. That's what we call static inference, meaning there's no motion, it's static, and it's with noise. The next thing we did, and this is going to be a movie, we moved the helicopter through the noise. So you're going to watch it here, you'll see it. And if you can see it, it sort of pops out, right? And you can see it pop out. Someone laughed about that. Now, when we show that to the HGM, it does a lot better. Much, much better, just like you did. And finally, we can do the same thing, but we can have the noise changing at every frame. So this is a movie where every pixel is changing every frame, OK? And watch, it's the same thing. And you can still see the helicopter in there. It pops out for you. It's not as easy as before. And sure enough, just like in a brain, we don't do as well, but we do a lot better than before. If I did these experiments today, we'd get 100% on this. This is 4 years ago. So this was encouraging for us. We said, well, maybe we're onto something. Maybe this is going to work. So now we've been spending a lot of time trying to make it realistic. And I'm going to give you a couple little demos here. I'm not going to do too many because we don't really have time for that. But I'm now going to try to do this in a demo fashion. What we wanted to do was, is that the one? Yeah. I hope you can see this. I can't make it any bigger. I apologize for that. I can do this, perhaps. That might make it a little bit easier. We now scaled this up to pictures, right? And we have a much bigger HGM and more complex and a lot of other stuff that went on there. And we can now feed it in grayscale images. Here's a picture of a sailboat. And on the right, you'll see this system only knows 4 things. You probably can't read it. It's sailboats, cell phones, rubber ducks, and cows, OK? So those are the 4 things. It's going to think every picture is one of those, right? So, but, you know, we start someplace. And this is actually very, very hard to do. I got to keep reminding you of that, because in case you think this is easy. So we can, in this case, I'm going to click here. I'm going to go to the next picture. And you'll see this is a duck, a rubber duck. And now on the right, it says, you may not be able to see it. The first bar has a duck under it. So that's a rubber duck. And it says, okay, here's another. Now, these are novel images. We never saw these in the training. We trained this on pictures and movies and so on. This says it's a cow. It knows that's a cow. Here's one. Here's a cow I drew on my whiteboard. Okay? I just drew a little square cow on my whiteboard, and I fed it, and it says, yeah, it's a cow too. Now, the things we can do here, for example, I can distort this. Now, every time I change this image, every time, it's sending it through this HTM again and calculating. This is all live. This is not a canned demo here. So I can zoom in on it and it says, yeah, that's a cow, that's a cow, that's a cow, that's a cow. So pretty soon it's going to start getting confused. Yeah, whoop, cow, maybe cell phone, I don't know. It's, you know, then it says, I'm lost. It says sailboat, I don't know. We can do also things like we can rotate it. And we can, it gets that correct. We can occlude it. We can put noise on it like this. Yep, cow, cow, and so on. So we have this test bed for doing these things. And the thing that Gar was just referring to, and hopefully I have it here, is we just shipped this tool that makes it real easy for anybody to do this. That you can create networks like this. This is a little flower network I have. And I'm not going to demonstrate this tool completely, but you can say, okay, you just take pictures of things. Here's pictures of lilies and daisies, and you just dump these pictures into this thing. You don't need to know any computer science. You don't need to know anything about brains. You train the thing on all your different images. This is what Gar's postdoc did. And then you can look for problems and debug it, and you can actually make computer vision things. Now, this isn't like human-like at all, and it's very far from that. But this is the easiest it's ever been to make a computer vision application. I think I can state that pretty clearly. And we're on our way going there. We've also can do the same thing with, just like we did with the little movies of the helicopter moving there. We're working with a company doing processing of video. And I won't show it here, but we basically can look at video scenes and look and try and detect what are people and what are cars as they move through the scene. These are things that haven't really been able to do very well up to now. Okay, we're going to go back to my presentation here. How am I doing on time? I'll show you one more vision thing we did. We started working with a company doing digital pathology. Now, digital pathology, they take high-resolution images of cell tissue. This is prostate gland tissue here. And trained medical doctors, MDs, have to look at these images looking for certain types of cell structures. They can spend up to 40 minutes looking at a single slide. Very big, high-resolution images. It's very costly and difficult to do. So we said, can we automate this process? So on the left here, you see 4 pictures of things that are glands in a prostate. On the right are 4 things that are not glands. And what makes a gland? Well, a gland has these black cell types. They're kind of surrounding a white vascular tissue area. But you can see they're quite varied. On the right, we have pictures that have black cells. We have white vascular areas, but they aren't quite in the right thing. Anyway, what we did is we did a little test like this. We ran it through our vision toolkit in some sense. And we trained on a couple hundred images, just one evening, actually. And lo and behold, it did really well. We got about a 95% accuracy rate. And the errors were reasonable errors. That is, where the places where humans might disagree as well. So now we're working with this company in really trying to bring this to market. And there's a lot of work to do that. I mean, it's not something you just plop it down like this. This is a simple test. To make it really valuable, you have to do a fair amount of work. So there's a lot of hope here for these things, these technologies. I want to remind you again, this is not just about vision. And we think this can be applied to lots of different things. In fact, I think it's sort of like a whole new way of doing computing. And there's a whole series of problems that people haven't been able to solve that humans can solve, and we think we can address some of them. Now, I want to end with a little talk about, is this dangerous? Now, I mention this because when Oppenheimer started the Manhattan Project, they knew it was dangerous. There's no question about that. They knew what they were doing, and they thought long and hard about the ethics of it and whether this is the right thing to do, and so on. And of course, a large part of the difficulty Oppenheimer got into later in life is that he was opposing the hydrogen bomb development when other people like Hans Bethe were not. And so there's a long history in physics, especially nuclear physics, about the dangers involved. Now, there's a fair amount of controversy here some controversy, I would say a fair amount. There's some controversy about this kind of work that we're doing. Is this dangerous? Are we going to create, monster robots and they're going to take over the world? And are we going to make monster brains that we can't control and things like that? There's some real serious people who are really worried about this. I just want to sort of characterize the problems a little bit with maybe a little tongue-in-cheek. There's a whole group of people who worry about what they call the singularity. And there's a book that came out recently called The Singularity is Near. This is by Ray Kurzweil. Ray Kurzweil is a very smart guy, but I think he's wrong about this one. The idea here is essentially that if we can create machines that are intelligent and more intelligent than humans, then those machines can create machines that are more intelligent than them, and then those machines can create more intelligence than them, and so you have this sort of runaway, chain reaction. Instead of protons hitting each other, we have, computers designing new brains and things like that. This is not going to happen. I'm just telling you, it's not going to happen. It's not like, what if I had a computer to design faster computers? Would we all of a sudden have infinitely powerful computers? No, there's limits to this stuff. And similarly, the limits to actually building intelligent machines have to do with the fact that you have to train them, and there's certain capacity limits, and it takes a long time to train them. And there's a whole series of issues here. I do believe we can build brains that are computer brains, artificial brains, or intelligent machines that are faster and higher capacity than humans. But it's nothing at all like a human. These are boring boxes like my laptop here. These are not emotional machines who have lust and sex and want to control the world and reproduce and all this stuff. These are just like, boring stuff. When they invented the steam engine, they used to worry that the steam engine, that was amazing. It was miraculous. And this is when people first started worrying about the, technology taking over the world. And the same thing happened when the computer was invented. It's not going to happen. Now, maybe somebody sometime will decide they want to try to mimic the rest of the brain, all the emotional centers of the brain, which we're not talking about here tonight. And maybe they want to try to build a humanoid robot like this thing down here. And, this is really science fiction. It's not going to be like that, maybe 300 years from now. I don't know. But it's not something that we're talking about here. We're just talking about building memory systems that can model different types of data streams, and that's all it is. There's this other sort of thing which I call it the matrix, or download your brain. And this little picture here, someone's got some ports behind their ear there. This idea that you can okay, we're going to become immortal. We're going to figure out how brains work, and then we're going to suck all the information out of your brain and stick it in some computer, and then you're going to be living multiple lives, and all this kind of weird stuff. This is not going to happen either. Is that a disappointment? I'm sorry. It's just not going to happen. You have trillions of synapses in your brain. And it's not like there's a binary code you can read out. Those synapses are complex biochemical things, and each one is located on a particular distance on a dendrite, and the transmission delays on those dendrites are critical to how your particular brain works. This is not going to happen. And, maybe it would be nice, but it's not going to happen. At least not in 100 years. Yeah, who can figure out about after that? Huge benefits to the world here from the fundamental physics that was done 100 years ago or 80 years ago. And I feel the same thing's going to happen with neuroscience. We're just on the verge. We're just starting to get started here. And I think in 20, 30, 40 years from now, this is going to be not only a huge industry and a huge area of scientific endeavor, it's going to be really beneficial for humanity to have ability to come to grips with who we are, how our brains work, and having machines that are really smart at understanding patterns and helping us as scientists and helping us as people discover how the worlds work. So there's always some danger to something, but I think the danger here is really, really minimal. If you're interested in learning more about this, there's several things you can do. You can read my book. I don't care if you buy it, borrow it, this doesn't matter, just read the book. You can go to our website, Nementa.com. You can sign up for a newsletter. You can download a whole bunch of these demos I just showed you. You can download the Vision Toolkit and make your own vision computer application. We have people starting to build iPhone and pre-apps now doing that. We have a very detailed product called NewPick, which is really technical, not for most people. And if you're a young person in the audience, I have two things for you. One is, think about making this a career opportunity for you, especially these scholarship winners here. Really, this is going to be one hell of an exciting place to be working over the course of your lifetime. And we do have a lot of interns at Nementa, so you're welcome to do that. And you can always contact me at this email address down here, jhawkins@nementa. So here I am. I'm really at the end of my talk, and I'm at the end of the time here. We have a lot of this. I found this nice picture on the web. I don't know if this shack still exists or where it was. But I thought it was fitting, sort of end picture here. You know, this, I just want to put my own thanks on this. You know, as a person who's never really been involved in what you guys do here, or at least, you know, this is a community, but we're also tightly associated with the laboratories here. I think the work that's been done here over the years and continues today is really wonderful, and it's great. And so I want to both thank you for what you do, and thank you for having me here. Thank you very much.